Students, today we are going to learn about sound. Sound is a form of energy. Sound is that form of energy which makes us hear. Each sound is special to the object which produces it. Sound is produced by vibrating an object. Sound can travel through a variety of medium at different speed. Production of sound in a tuning fork. Production of sound in a tuning fork. This is the stem of the tuning fork and these two are the prongs of the tuning fork. Vibration of the tuning fork. Striking the tuning fork. When a tuning fork is struck, it begins to vibrate typically at a frequency between 100 Hz to 1000 Hz, depending on the size and design of the fork. Movement. As the tuning fork vibrates, the prongs move back and forth, alternately compressing and rarefying the air around them. This creates sound waves. Production of sound by tuning fork. This is the tuning fork, and this tuning fork is kept stationary and it has a two prongs. These two are the prongs and this is the stem. And this to show the state of air around the tuning fork. These vertical lines are used. These are the vertical lines and this shows the state of air. Here the vertical lines are equally spaced. Vertical lines are and it indicates vertical lines are equally spaced. It indicates that the average distance between the air molecule is the same everywhere and the average air pressure in three regions A, B, C is also the same. Now if the stem is kept steady and prongs struck, this are to kept steady and this are to struck on the rubber pad, then the prongs are set into vibration. These prongs are set into vibrations. It means that they are set into periodic motion in forward and backward direction. And we will see the step by step result of such a motion. If during the vibration, if the air molecules outside the prong is compressed, this is called compressed region. Compressed and the pressure there increases. Here the pressure is more. The pressure increases. Such a state of high pressure is created in the region A. This is the region A. High pressure is created. And the region which air is at high pressure and density also more here and pressure is also more and such region is called compression. And in the next step the vibration of the prong come close to each other. Here see this come close to each other. These prongs come close to each other and in this case the air molecules near the prongs are get more space. Here air molecules near the prongs are get more space and to move away from each other. As a result, the air pressure in this region decreases. In this region the air pressure is decreases and such a region is called The density also very low. This is region is called rarefaction. This region is called rarefaction. Here also in this figure, this is the compression, rarefaction. This is the rarefaction, this is the compression. The frequency of sound. Frequency of sound waves refers to the number of oscillations or vibrations of air, particles or other mediums per second, and it is measured in hertz, where 1 hertz is equal to 1 cycle per second. The frequency determines the pitch of the sound, how high or low a sound is to be perceived to be. And this region shows the one oscillation, one compression, and this is the rarefaction. This is the one oscillation. Here density also more, here density is less, and one oscillation consists of compression and rarefaction. How the motion of air molecules due to sound. This diagram shows that cycle of compression and rarefaction. And sound waves, in the sound waves, the change in air pressure also. Amplitude of vibration. The amplitude of vibrations determines the loudness loudness of sound. The larger oscillations create louder sounds, while smaller oscillations produce softer sound. And this shows the amplitude. This is the amplitude of vibration. This is the length. This, okay. This is the amplitude. This called this length. Larger the oscillation gives more, and this creates the amplitude of vibration. Okay. Now next is wavelength and frequency. The frequency of the tuning fork determines the pitch of the sound. The longer the frond of the fork, the lower the pitch. That means longer the wavelength. This is called one wavelength. This is the one wavelength from peak to the peak, and this is the amplitude, this is the trough. Okay, longer the wavelength, while a shorter frond produces a higher pitch and shorter the wavelength. Okay, shorter, that this is called one wavelength. That means the frequency of the tuning fork determines the pitch of the sound. That means the longer the prong of the fork, lower the pitch, the longer the wavelength. If the pitch is lower, wavelength is longer, and if the pitch is shorter, the wavelength is also shorter. This is called the wavelength. Propagation of sound and medium. And in this experiment, as the air is pumped out, the sound of the bell becomes fainter and fainter. Eventually, when most of the air is removed, creating a near vacuum, the sound of the bell becomes inaudible, even though you can see the bell vibrating. Explanation of this experiment. Why does the sound disappear? Sound waves are mechanical waves, meaning they need a medium like air, water, or solid object to propagate. When the air is removed from the bell jar, there is no medium for the sound waves to travel through. Without a medium, the sound cannot reach your ears. What does this demonstrate? This experiment demonstrates that sound cannot travel through a medium. It highlights the importance of a medium for the propagation of mechanical waves. Sound and music. Jalatarang. The Jalatarang is a traditional Indian musical instrument classified as an idiophone. It consists of a set of ceramic metal bowls filled with water to varying levels. The levels of water in the bowls determine the pitch of the sound when stuck with wooden sticks or mallets. The word Jalatarang translates to waves in water in Sanskrit, the reflecting the instrument's unique way of producing music. Key features. Typically, a set of 15 to 22 balls is arranged in a semicircle or in a straight line. A tuning by adding or removing water, the pitch of the each bowl can be adjusted. The musicians strike the edge of the bowl with the sticks, creating melodic, resonant tones. When a cup is struck, the waves are set up in the air column above the water level in the cup. The frequency of the generated wave depends on the height of the air column inside the glass cup. The instrument produces a soothing bell-like sound that is rich in overtones. A Jalatarang has been mentioned in ancient Indian text, including the Nastya Shastra by Bharata, has one of the oldest instruments used in Indian classical music. Over time, its popularity declined, but it remains an integral part of certain classical and folk music traditions. Jalatarang. The musicians strike the edge of the bowl with the sticks, creating melodic, resonant tones. When a cup is struck, the waves are set up in the air column above the water level in the cup. The frequency of the generated wave depends on the height of the air column inside the glass cup. Since the water level in each glass is different, the height of the air column in each glass is also different. Therefore, frequency generated in each glass cup is also different. And we will clearly see in this video the how the frequency is generating and how the sound waves are creating.